Hello everyone and welcome on today's video. My name is Wouter Peer, I'm the founder and main developer of GHEtool Cloud. And today we will be going over the concept of the simultaneity factor. Now this factor is really important when it comes down to the design of large geothermal bore fields. For example, in the case where you have an apartment building with multiple units where each apartment has its own heat pump, but it's all connected to a central bore field. So let's first discuss what this factor is and why it's important for your geothermal design. Now imagine you want to design a bore field for a single building. And we know that the building has a 10 kilowatt heat pump and it has an energy demand for heating of 50 megawatt hours per year. Now for the apartment building, we for example know the energy demand and the heat pump for each unit. So we can, for example, know that we will have 25 apartments with each having a 5 kilowatt heat pump, giving us a total installed power of 125 kilowatts. For our energy demand, we also know that, for example, an apartment has 7.5 megawatt hours per year of heating demand, multiplied by 25 gives us almost 190 megawatt hours per year. So this is the information we typically have available. Now, if we design the bore field for the single building, we know that we will design it with a heating demand peak of 10 kilowatts. Now, for the apartment building, we can design it with 125 kilowatts, but perhaps we can design it with a little bit less. And this is due to the simultaneity. So the concept is that when you have multiple units connected to a central bore field, the peak powers, the 5 kilowatts for each unit, they do not occur at the same time. Because the occupants of each apartment are also different. Some might be elder people, some might be younger, some have children, some have not. So due to this difference in occupancy behavior, the peak power does not 100%, is not 100% at the same time. And this is what's called the simultaneity. So this is a curve which was based on the work of Winter et al. In 2001, where they studied district heating networks with a small and a larger number of users, and where they knew the total installed power, and they also measured the power that's actually coming from the grid. And what they noticed is that depending on the number of users, or when the number of users or units, etc. Increased, the simultaneity, so the percentage of your total installed power that occurs at the same time, it decreases. So for example, if we have 100 units connected to a system, we know that only 60% of the total installed power will occur at the same time. In our case, where we said, well, we have 25 apartments, we see that we have 89% of simultaneity, which means that a geothermal bore field will only experience a peak power of 111 kilowatts. Now, this of course is depending on the number of units, etc. But one question that remains is what to do with the peak duration of your system. Now, to give you a little bit more insight in the simultaneity factor, it was originally developed to design pipe diameters. So if you have a district heating system and you know 100 users are connected, you want to size your pipe in such a way that you make sure that your peak power can pass through it, or also that your central heating, you want your central boiler, for example, or waste incineration plant, whatever, can actually heat and provide the buildings with their peak demand. So you just need to know, okay, if we have a certain amount of people, a certain amount of connected users, what's the maximum amount of peak power that can occur? It does not really matter originally or historically how long that peak, what the duration of that peak was. If it occurred for 1 hour or for 100 or 1000 hours, that was just a matter of the fuel or the energy demand. It was not that important how long the peak duration actually was. But for our geothermal bore fields, this is important. For example, if you size with a monthly resolution, which is the case in most simulations, we need to know the peak power for heating and also for cooling, but let's now focus on heating. We need to know the peak power which can happen in the year. And this we know due to the simultaneity factor. We can reduce the total installed power with the simultaneity factor down to the peak power that can actually occur. So that's done. Second thing is the energy demand, because we need to be able to calculate the imbalance. And this we also have because it's just the summation of all the different energy demands of our units. And by using the simultaneity factor, we're not decreasing the energy demand, because that's a given. We're just decreasing, calculating what the resulting peak power of our total collective system will be. So energy demand we also have. What we do not have is the peak duration. Now, to go a little bit more deeper into that and why it is important, the peak duration for both heating and cooling, it's defined as how long does the peak power occur without interruption. So to put it otherwise, if the heat pump jumps on and it works at maximum power, how long will it keep working in maximum power? And this has an effect on the maximum and the minimum average fluid temperatures. Like, for example, we discussed earlier that a borehole effective thermal resistance also has an effect on this peak power. But of course, you can imagine if your heat pump runs for 2 hours versus for 10 hours straight, that the situation in which it runs for 10 hours, it will end up with lower temperatures because you're putting more demand onto your bore field after in one continuous run. So this peak duration is important. Now, if you, for example, have this situation, so I have here 3 different buildings. We have a yellow building, a greenish building, and a pink or red building. And each of these buildings are connected to a collective heating system. And this is the power we see here. And we see that the yellow building, it has a certain peak duration, let's say 8 hours, and the green one and the pink one also. But the peak does not coincide. So the resulting peak we can get is this blue line, for example, where you see it's higher than the individual ones, of course, but it's not the sum of the individual ones. So that's the simultaneity factor. But we also see that our peak duration, it's not the same as the duration of the different ones combined. So to calculate the peak power of our collective system, we cannot just simply take the sum of all the peak durations, because that will be an overestimation, especially if we go to 100 or more systems. But we can also not say that the duration of our collective system is just equal to the duration of one of the individual components. Because if we're combining the systems together, we end up with a peak power that's lower than just the sum of all the different ones, but the duration is also longer, of course. So how do we cope with this second challenge when it comes down to the design of collective systems in geothermal borefields? Now, one solution, which is actually the best, is to do a dynamic simulation of your building. So you simulate your apartment building, then you end up with an hourly profile. And since you now have an hourly profile for heating and cooling, you don't need to make an estimation of the peak duration, because it's embedded in your hourly demand profile, let's say. So this is, of course, ideally the best solution. Now, a second option, for example, in feasibility studies, etc., is to use an heuristic, an estimation, let's say even a correlation, to convert the peak duration of a single user towards the peak duration of the collective system. Now, the problem with this heuristic approach is that there is no real literature about it. So regarding the simultaneity factor, there is quite a lot of literature because it have been used in the past, but related to the peak duration, which is really typical to the geothermal borefields design, there is no real literature. So what we can say is that as a first approach, we can base us on the central limit theorem, which is very important in the statistics domain. And although the derivation is outside the scope of this video, it can be used to say, well, if we have a peak duration of our individual building and we multiply it by the square root of the number of apartments or heat pumps or units, whatever, we can come up with an approximation of the peak duration of the collective system. Now, I want to stress that this is a first approximation. It should be used with caution because there is no real literature or quite a lot of evidence for this equation, at least in the geothermal borefield design. But what it will tell us is that in the case, for example, for 25 apartments, and just to recall, we had 125 kilowatts installed power, we had almost 190 megawatt hours per year in heating demand, and we typically have a peak duration of 8 hours for each unit. Then we can convert it towards our collective system, which has then 111 kilowatts of peak heating due to the simultaneity factor of 89%, which we saw earlier. We know that our energy demand is the same, because as we said, we do not change the energy demand, we're just changing the resulting peak power, not the installed one, but the resulting peak power for our borefield design. And then for our peak duration, we see the scaling factor here, just the square root. For our 25 users, we have a scaling factor of 5, so we end up with a peak duration of 40 hours, which might seem like a lot, but of course these type of heuristic approaches, they scale and they will become more accurate, let's say, when you have more users. So for example, if you have 100 connected users, your scaling factor for your peak power is 10, but your simultaneity factor, if you would scroll back, it's around 60. So perhaps for smaller systems, this is a little bit on the safe side. For bigger systems, on the other hand, it looks more reasonable, let's say. So I want to conclude this video here. It's a more theoretical explanation again. In the next video, we will take a look at some examples in GHEtool where we will discuss a little bit more about the difficulties and the challenges when working with the simultaneity and peak duration factor. We will for sure keep you updated on new research on this topic, and we also plan on implementing this directly into GHEtool when there is more evidence to support actually this peak duration curve. So I hope you have found this video interesting. Please consider subscribing, sharing this with your colleagues, other companies as well, and I'm looking forward to seeing you in the next video. Take care. Bye.